we're getting close to the end in our discussion of the 5 general types of chemical reactions. And in the big picture, we're going to see that there's only 2 types of chemical reactions, at least at the early stages. And those are double replacement and oxidation reduction. Well, here we have double replacement reactions today. And in a double replacement reaction, we have 2 ionic compounds where the cations or anions are switching places. And we'll compare that to our single replacement reactions in a second, right? We've got 2 ionic compounds. And in those compounds, you're going to switch cations, we will say cations or anions. It depends on how you want to look at it, right? And they're going to switch cations. And then in parentheses, I'll put anions. And it really doesn't matter which one you choose. It means the same thing in the big picture. All right. Now, with single replacement reactions, we had something by itself and something in a compound, and something by itself could replace the thing in the compound if it was higher on the activity series. That was a very nice tool for predicting whether or not the chemical reactions were going to take place. For double replacement, we can't do that because we don't have something by itself. But the nice thing is we have a different type of tool available. We're going to look for what is called a net ionic equation, all right? So in order to predict if a double replacement reaction is going to take place, we're going to look for a net ionic equation so we can predict if a double replacement reaction, and I'll abbreviate that, double replacement, predict if a double replacement reaction will take place. And we're going to do that by looking for a net ionic equation, all right? All right, so the question is, what is a net ionic equation? And the maybe unsatisfactory answer is that the net ionic equation is what actually happens, right? The net ionic equation is the actual reaction. And you may say, like, oh, isn't everything the actual reaction? No. It turns out that some things are there to balance charge, and we call those things spectator ions. And so we may as well take care of that right now. So we're going to remove any spectator ions. All right, so the idea with it is this. If you have a net ionic equation, then things are actually reacting. And the things we don't care about are the spectator ions. Spectator ions are there to balance charge, all right? They're not there to do any reacting. So what we see with spectator ions, and I'll move this over here right now, is that the spectator ions appear unchanged from reactants to products. All right, so that's how we're going to spot them, is they remain unchanged from reactants to products. Now, the question is, like, how do we look for a net ionic equation? And the answer is there's a fair bit of work involved. And we're going to have to do some refreshing of a couple terms before we can get there. And the terms of interest, or the things that I really want to note here, is we're going to make use of some solubility rules, all right? So we're going to have to utilize our solubility rules. And what we're looking for are aqueous and non-aqueous species, right? So we're going to utilize the solubility rules to identify aqueous species. And if you remember, or if you don't, AQ for aqueous literally meaning in water, right? And so these aqueous species, when we're talking about ionic compounds, are what we call electrolytes, right? And that's terminology that we're going to get way more in depth in another video. But these aqueous species are our electrolytes, at least for these double replacement reactions. And those electrolytes dissociate. And you may or may not remember that term from when we were talking about the components and the symbols in chemical reactions and chemical equations. But to dissociate is to separate into ions. Specifically, in our solution. All right, so this is going to be a key idea here, is our aqueous species are going to dissociate, okay? So let's take a look at some examples and we'll see how this works out. The key things that we're going to be doing, there's 3 basic steps or 3 things we're looking for. We're looking for a complete balanced chemical equation. We can't get away from that. We're looking for a complete ionic equation, which separates everything into their aqueous species. And we're looking for a net ionic equation, which is showing the things that actually react. And we'll be utilizing something like this, a set of solubility rules, to predict what's going to be aqueous and what's not, what's going to precipitate out of the solution. All right, so let's come up with a simple example here, and this is a classic one in like every classroom ever, which is the reaction of lead nitrate, and we'll say it's lead 2 nitrate. And I'm going to put open parentheses right there. That's something we're going to have to fill in a little bit. And we're going to react that with, or we're going to mix that with, maybe potassium iodide, and that will be in our solution one way or another. We're expecting to switch cations or anions, however you want to think about it. You can think of it as the lead and the potassium switching places, or you can think about it as the nitrate and the iodide switching places, but the result is the same, all right? So if we look here at the lead, that would be, we would make up a 2 plus, right? 1 plus, 1 minus, 1 minus. So we are going to switch these. I'm not going to ask the question like we did with single replacement of, can it happen? The answer is going to be, we're going to say they switch, okay? And then to get our formulas on the other side, we're going to have to remember to crisscross charges. Like I can't escape this idea because people keep avoiding it, which is when you get to the other side, this subscript has no meaning because this subscript says how nitrate reacts around lead, how it behaves around lead. And on the other side, it's not going to be with lead. It's going to be with potassium in this case. So I'm going to have a compound that has potassium. That's a 1 plus. And nitrate, which is a 1 minus. Crisscross and reduce, we get KNO3. I'm going to throw some room for my phases in there. And then we've got the lead now with the iodide, and the lead is a 2 plus, and the iodide is a 1 minus. So we crisscross and reduce, and we get a 2 right there. And I'm going to put my parentheses. We do need to balance it, and I am going to show the work. I know everyone's tired of that at this point, but I said we have to do it, and we're going to do it, right? That is how we convey to other people what we've been doing. In this case, I've got lead. Keep your polyatomic ions together if you have that option, which we do because they're on both sides, potassium and iodide, right? So on the reactant side, we've got 1, 2, 1, 1, and on the product side, we've got 2 of these, 1 potassium, 1 nitrate, and 1 lead. If you didn't notice, it's not balanced, and we can see that right there. We're going to double whatever has the nitrates. That looks good there, but it screws up the potassium, which is okay, because when we fix that with a 2 and a 2, now it's balanced, and we can see all that work. All right? Nothing new at this step. Everything we've done so far is just completing and balancing a chemical equation. Now we know we're going to call this a double replacement reaction. We can spot it as such because I have an ionic compound and an ionic compound. And if you're saying, like, well, how do I know it's an ionic compound? Short answer, you've got a metal with a nonmetal, a metal with a nonmetal, or some compound with a polyatomic ion. So we've got a metal and a polyatomic ion. Either one would tell you it's ionic. We've got a metal, potassium, and a nonmetal iodine. So 2 ionic compounds, double replacement reaction, that's what we're going to look for. We need to fill these in. And up until now, we've avoided that, but we can't avoid it anymore. And here's how we're going to fill those in. We're going to assume that we have water. These are solutions we're working with. And we're going to look for some key things, right? The idea of soluble, right? What does it mean to be soluble? It literally means to dissolve in, right? So soluble is going to end up aqueous, since we're talking about having water. And insoluble means it's not soluble. It won't dissolve in. So we're going to have solid, right? Or liquid, it turns out. So that's what we're going to be looking for. Our aqueous, solid, or liquid is what we're going to fill in those blanks with. And I'm just going to highlight a couple things on here, the things that I look for every single time. So you're not going to memorize these, there's no point, but like theoretically given a table or theoretically doing enough of these, you'd remember the rules. And like I don't bother remembering a lot of the rules, I basically remember that group 1 metal compounds are always soluble. So if you got a group 1 metal, always soluble. And nitrates are always soluble. And chlorides, bromides, and iodides are soluble unless you've got one of those things, all right? Anything beyond that, like that'll cover in just general examples, probably like 2/3 of the examples you might come across. So with a little practice, you remember those, doesn't matter though, and then the other ones you can check. So here is my policy. check for nitrates. Oh, there's a nitrate. That's going to be aqueous, right? And if that sounds suspicious, like literally that is what I do. Oh, there's a nitrate. That's going to be aqueous, all right? Oh, there's a nitrate. That's going to be aqueous, okay? And what we're saying is compounds that have nitrates are going to be soluble in water, period, okay? Then I'm going to look for group 1 metals or chlorides, bromides, and iodides. And as I look here, potassium is in group 1 of the periodic table. It's a group 1 metal, so that's going to be aqueous. And then I've got all of these taken care of. And take a look here. Nitrate or potassium would have told me aqueous. And then I've got lead and I've got iodide. So no rules about lead or iodide. No rules about lead or iodide. Ooh, there's an iodide. And it's going to be soluble unless I have lead, silver, or mercury. And I happen to have lead, right? So once again in slow-mo, there's an iodide. It's going to be insoluble with lead. Lead happens to be one of the exceptions. So it's going to be insoluble. A solid is what we put, all right? Critical step, we've done all the heavy lifting. These things that I added in red came from our solubility rules, and you kind of just got to be able to read that table and plan ahead for some common ones. Now we're dealing with this idea right here. We're going to dissociate stuff. We need to separate it into ions. There's many, many, many ways you can do it, one of which is to just look at it and write it. But I think it helps in advance to go through and kind of identify what pieces you have, right? Lead is a piece. Nitrate is a piece, and I have 2 of it. Potassium is a piece, iodide is a piece, and I have 2 of each of them, all right? Potassium is a piece, and nitrate is a piece. I have 1 of each, times 2 is 2 of each of them. And then lead iodide, I'm not going to separate because it is solid. So that's the basis of how this works. We're going to take our complete balanced chemical equation and we're going to turn it into a complete ionic equation, right? So this thing that we just wrote is our complete balanced equation. And I guess I could write the word chemical. And what we need now is our complete ionic equation. And I'm going to write all this out and then I'll write next to it the complete ionic equation. And to do it, you need to dissociate everything that is aqueous, all right? And I'm going to write that down in a minute, but let's look again. Aqueous, break it apart. Aqueous, break it apart. Aqueous, break it apart. Not aqueous, leave it alone. That's what we're doing. That's the basis. So I've already listed what my pieces are going to be. So let's take those pieces, and I know I'm getting marker color blind here. There's just too many options. But I'm going to take this, right? And this, and this, and this, and this, and this, and I'm just going to bring that whole thing down. And if you can't see the yellow marker, that's actually kind of funny, but you'll live. So we've got lead ions. And we've got nitrate ions, right? And I have 2 of them, 2 nitrate ions. And they are aqueous. I've got 2 potassium ions, and I've got 2 iodide ions. All right, I screwed up my arrows. I've got 2 potassium ions and 2 nitrate ions. And I've got that lead iodide that didn't dissociate. Okay? We do keep our phases in, and there's a few things that I want to point out. And one of them I harp on and harp on and harp on with my students, and that's charges, right? Like, do we need to put the charges? That's more work. Yes, you do. And there's a simple reason why. So, yes, we need to put the charges with the ions, yeah? It's a life or death situation is how I describe it. If you look at potassium metal is very reactive, and if you were to eat it, it would probably burn your tongue chemically and burn it thermally because it's exothermic when it reacts with water. That'd be bad, right? And if you somehow got a chunk of potassium down to your stomach, it would either kill you or make you very, very, very sick. So potassium would kill you. We're just going to declare that. Potassium ions you need for survival. Your muscles work on sodium-potassium pumps, right? That's potassium ions that you're worried about. So you need potassium ions to stay alive, and potassium metal would kill you. You need it to stay alive, it would kill you. You need to stay alive, it would kill you. That's how important the charges are. K plus, the potassium ion, is not K, potassium. K, potassium, is a metal, right? And potassium ions aren't metallic, right? And we could get potassium ions in our diet from things like, they often say bananas, or whatever else. Anyway, charges, yes. And the other thing that I do expect to see all the time are those phases. And if it was aqueous up here, it's aqueous down there, right? And I guess I can highlight that. Aqueous, aqueous, and then solid becomes the same thing. So there's two key ideas that we've got. Break everything apart, keep the charges, keep the phases. If you don't, you're being negligent, and you're cutting important corners that we can't afford to do. As you look at it, then, we need to look for spectator ions. I promised you it would say right here, this is what we call a complete ionic equation. And what we have done is we're going to dissociate any aqueous species, all right? So we have dissociating any of the aqueous species from our equation. Our complete and balanced chemical equation, okay? Done. Now we want to come up with a net ionic equation, and we're going to do that by eliminating spectator ions. How are we going to identify our spectator ions? Well, spectator ions are things that remain unchanged from reactants to products. As you look here, do we have any of those things? Well, since I highlighted this in yellow, I'll look here. Do I have lead ions on the other side? No. No. Not lead ions, it's in a compound, right? So that is something that is not a spectator. Do I have any nitrate ions on the other side? Well, no. Yes, I do. And by the way, those numbers have to match. If it was balanced here before you dissociated it, it needs to remain balanced here. It will remain balanced here. So if you did something like forgot that little subscript 2 down there, you'd catch it as you looked left to right. All right? So I'm just going to cross out this spectator here. In highlighter, it's gone for our purposes. Do I have any potassium ions on the other side? Why, yes, right there. That's a spectator. What we are saying is, on this side, it was a nitrate ion. On this side, it is a nitrate ion. It didn't change, so nothing happened to it, right? That's a spectator. If you go to a sporting event, you have spectators sitting in the stands. They don't do anything that affects the outcome of the game. And then you have the athletes who are actually involved in the game, and they are changing things. So iodide, part of a compound. It has changed, right? So this, and this are going to form our net ionic equation. So I'm going to take those things, my lead ions, and the nitrate ion, my iodide ions, and that's going to give me lead 2 iodide. Something happens, and in this case that something is precipitation of lead 2 iodide. It happens to be a very brilliant yellow color, and I wish I could show you, but it's not an option right now. So this right here, we will declare this is our net ionic equation, right, which is our actual reaction. And I always say, in this particular situation, something like this, it's like you have lead ions and nitrate ions in one beaker, and then potassium ions and iodide ions in the other beaker, and then you dump them together, and you have a beaker with potassium ions and nitrate ions, and then the lead iodide is settled out to the bottom. I've never drawn that before, but I guess I could try. Inevitably, it's going to be a disaster. So we'll just say I've got some beaker here, right? And another beaker, and these have some aqueous solution, right? So, and in this beaker here, maybe I've got my lead ions and my nitrate ions. Those are aqueous. And over here, I've got the potassium ions and the iodide ions, which brings up another important question about the Hofbräuchel, the diatomics. And then in the end, I'm going to mix these together into one beaker, and that beaker is going to have most of the aqueous solution. I hope my dog snorting in the background isn't making too much noise. In that solution, I'm still going to have my potassium ions floating around. I'm still going to have the nitrate ions floating around, right? And then on the bottom, I'm going to have this lead iodide precipitate. It's not in the solution, all right? It is a powder that has settled to the bottom. So this is our PbI2 solid, all right? And that's semi-visible. In the beginning, we've got two beakers. Looks like water, tastes like death. Clear, colorless, clear, colorless. I dump them together and I get a clear, colorless solution with a yellow powder that falls to the bottom. In the solution, I have potassium ions and nitrate ions. I don't have any of the lead or the iodide because those things precipitated out. I'm not that disappointed with how that picture turned out. All right, something that I promised I would mention moments ago is this right here. It's a very, 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 very common question to say, like, this is iodine. When it's by itself, why don't we make it diatomic, right? Like, that's something we drilled into your heads, is this idea of Hofbrinkel, things that are diatomic by themselves. And iodine's one of them. And there's a simple answer. That is iodine by itself in its elemental state. This is iodine in a compound. This iodine in a compound is an ion, and it's a 1 minus, all right? It's not elemental iodine, which has 0 oxidation state. In a compound, has a charge, and we have 2 of them, all right? We don't have I2, diatomic iodine. I want to do one more, and then I'll do several examples in another video, but let's see what we can do for a second example right here. We'll take, having a color crisis, maybe some magnesium nitrate and aluminum bromide. Let's give that a try. I guess if we're going to keep with our color convention, magnesium nitrate. And the way I'd get that formula is by crisscrossing and reducing. Magnesium's a 2 plus, nitrate's a 1 minus. I'm going to put my parentheses indicating that the phase is soon going to be on there. And I'm going to mix that with maybe like aluminum bromide. And I crisscross and reduce. There's a 3 there. And that's going to give us something. So, step 1, identify what type of reaction you have. Metal and polyatomic ion, that's ionic. And metal and nonmetal, that's ionic, all right? 2 ionic compounds, most likely double replacement. We're expecting things to switch places. And those things that might switch place, you can treat it as the anions switching places or the cations switching places. It doesn't matter as long as you don't try and switch both, in which case you're back where you started, right? If we put the magnesium over here and then we put the nitrate over here, you'd be back where you started. Key idea, and I know I say this over and over and over, when you get to the other side, you need to crisscross and reduce. This 2 has no meaning when we get to the other side. This 3 has no meaning when we get to the other side, because this 3 is how bromine interacts with aluminum. This 2 is how nitrate interacts with magnesium, and when nitrate's with aluminum, it might not interact the same way. So we'll get those formulas by crisscrossing and reducing, right? So if I've got a 3 plus and a 1 minus, I'm going to need 3 of those to leave room for our phases. And then I've now got the magnesium with the bromine, 2 plus. Br is 1 minus. We've got a 2 right there, and I'll leave room for my phases. We should balance it, I suppose, and we've got magnesium and nitrate and aluminum and bromine. 1, 2, 1, 3. It's not balanced. 1 aluminum, 3 nitrates, 1 magnesium, and 2 bromines. So, again, looking at the big picture, we can predict there's going to be like some 6s involved. We're probably going to have to put a 3 there and a 2 there. And I know I've gotten lazy and I'm cutting corners, but we got to keep the show on the road here. 3, and we've got 6 nitrates then. And on the product side, we've got 2 aluminums, and we've got 6 nitrates. So we're getting closer. We're going to need a 2 here and a 3 here. That'll give me my 2 aluminums and my 6 bromides and my 3 magnesiums and 6 bromides. All right, it's balanced. We know it's balanced because the work shows it. Now I need to add in these phases right here. And we said the way we're going to do that is to look at our solubility rules. And the key things I'm going to look for right away are nitrates. Do I have any nitrates? And there's a nitrate. Whatever it has, it's going to be aqueous. Nitrate is going to be aqueous. I don't even look at what the cation is. If I've got the nitrate, I'm going to put aqueous. Other things I'm going to look for. Group 1 metals. All right, so group 1 of the periodic table. No. Okay, so that's out. I'm going to look for chlorides, bromides, and iodides. No. There's a bromide. Okay, it's going to be aqueous. This compound's going to be aqueous unless the metal is silver, mercury, or lead. And it's aluminum, so we're okay. That's going to be aqueous, right? And then we've got this magnesium bromide. Hey, it's a bromide, and we're expecting that to be a soluble compound unless it has silver, mercury, or lead. And it doesn't. Magnesium is not silver, mercury, or lead, so we have something that is aqueous. All right? And we labeled these before, and I'll label it again. This is our complete balanced equation. We need to dissociate all aqueous species, right? And I think that's an important thing for us to note. To get the complete ionic equation, we're going to have to dissociate all of our aqueous species. These blue Sharpie highlighters are like continually a disappointment to me because out of the box, they're both dry and non-functional. Shame on you, Sharpie. As we look here, you don't have to do this step, all right? In fact, I'm going to flip this over so that it covers up our previous work. You don't have to do this step, but I don't think it hurts, and that is identify what your pieces are, all right? I've got magnesium, that's a piece of my stuff. I've got nitrate, and there's 2 of them. I've got aluminum, and there's going to be 2 of them, and I've got this bromine, and there's going to be 6 of them, right? 3 of those, 6 of those, sorry. The aluminum's right there, I'm going to have 2 of, and the nitrate's right there, I'm going to have 6 of. Magnesium and bromine, okay? And if you're paying attention, something's about to happen, and you might be able to predict how this is going to go. I'm going to take these things and dissociate them. I guess I could try and space things out a little better than I did last time. The magnesium and the nitrate. The aluminum and the bromide. The aluminum and the nitrate. The magnesium and the bromide. Let's see if I budgeted my space a little bit better. We've got 3 magnesium ions. Those are aqueous, all right? And I've got 2 times 3 is 6 nitrates. That's aqueous. I've got 2 aluminum ions and 6 bromide ions. And the good news is, like, if you're not noticing that this 3 times 2 is 6, you'll catch it left to right as you're double checking your balancing. I've got 2 aluminum ions, and I've got 2 times 3 is 6 nitrate ions. And now we've got our 3 magnesium ions, and 2 times 3 is 6 bromide ions. All right, so that is our stuff. We need to just address a couple things. The first thing is, like, why wasn't this a Br3? And the answer is because each Br is a 1- to match up with the aluminum's 3+. I have 3 of these things that are 1-. I have 3 times 2 gives me 6 of those things that are 1-, all right? So that 3 is a coefficient because it is not part of this piece. It's just telling us how many of that piece we have. Just like that 2 is telling us how many nitrates we have. And that 3 is telling us how many nitrates we have. This 2 is telling us how many bromides we have. As opposed to a situation like the nitrate, to be part of the polyatomic ion nitrate, you need 3 oxygens and 1 nitrogen. And those 3 oxygens are part of this. It's one thing, 1 nitrate, that has 3 oxygens, all right? Whatever. As we're looking for spectators, this is our complete ionic equation. So to get from our complete balanced equation to our complete ionic equation, we dissociated all the aqueous species. And that got us our complete ionic equation. To move down to this next step here, we're going to remove all of our spectator ions. And the spectator ions, we said, are the things that remain unchanged from reactants to products. And we'll see what it looks like. I have magnesium ions, and I have magnesium ions. That is a spectator. It has not changed from left to right. I have nitrate ions, and I have nitrate ions. So that has not changed from left to right. I have aluminum ions, and I have aluminum ions. Those have not changed from left to right. And I have bromide ions, and I have bromide ions. Those have not changed from left to right. So I'm going to take everything that I didn't cross out, and that's what's actually happening. That's my actual reaction. Oh, that everything crossed out. So you may note here there's no net ionic equation, right? And what that means is, and the 3 dots in shorthand is therefore, there's no net ionic equation, therefore there's no reaction. All right, no net ionic equation, therefore there's no reaction. So I want to go back to a version of my spectacular beaker drawings. So this was what we had previously. I'll try and fit that on the screen. And this is how things would look this time. That's a beaker. Beaker that I'm going to put stuff in. They are aqueous solutions, so I'll draw some layer of liquid there. On this side right here, I have my magnesium ions and my nitrate ions. So I'll put the Mg2 plus aqueous and NO3 minus aqueous, right? And on this side, I have the aluminum and bromides. So I've got aluminum ions and bromide ions. All right? And so what am I going to have when I'm done? I'm going to have magnesium ions, and I'm going to have aluminum ions, and I'm going to have nitrate ions, and I'm going to have bromide ions just floating around. So in the beginning, I had a beaker with some ions, I had another beaker with some ions, and I dumped them together, and I had a beaker with 4 ions. All right, that's no reaction has taken place, but we have a neutral charge, so that's what has stayed true. And as opposed to this one, where something changed, we got to precipitate in the form of that lead iodide. So again, our key distinction here, we had something that changed, right? The lead ions turned into part of a compound that was not aqueous. It did not dissociate. The iodide ions turned into a compound, part of that lead iodide. It did not dissociate. Something changed from left to right. In this side, everything left to right stayed the same. Nothing happened. There was no reaction. Okay? So that's the basis of double replacement. I'll do another video that has more examples of this. Specifically, I want to see an acid-base reaction where instead of a solid here, we end up getting a liquid, and that's water. And that's kind of interesting because for acid-base neutralizations, they all have the same net ionic equation, at least for strong acid, strong base problems.